Here's another really interesting example of a surface tension, or at least the effects of surface tension. It turns out surface tension causes water to appear in drops. Of course, everybody already knows that, but probably didn't think about the fact that it was because of surface tension. If you think about it, here's a drop. Let's say we have a water drop, and along the surface, it's kind of like a skin. The surface of the water forms like a skin, and the molecules attract one another. And since, if you think about it, a molecule in the middle gets attracted in all directions, so there's no net force acting on this molecule, but a molecule at the very edge will feel forces inward like this, and along the edges, but not towards the other side. And so that means is that the water molecules on the edge are being attracted inward, and so it forms a spherical shape. And because of the surface tension, there's a certain amount of pressure that builds up inside a water drop. And so what we're going to try and figure out here is, what is that pressure of a water drop? And of course, that also will depend upon the size of the water drop, as you'll see in just a moment. So let's say, how big should we make our water drop? Let's make it a radius of, let's start with a 1 centimeter water drop. That's a pretty big water drop, isn't it? Now, just for the sake of argument, let's say that we start out with the radius equals to 1 centimeter. What would be the increased pressure inside the water drop as compared to outside the water drop? All right. So again, the force due to the surface tension is equal to the coefficient of surface tension times the length along which this acts. Now what we're going to do here is we're going to take a water drop and slice it in half. And so you think about these two halves separated from one another, and of course they would be attracting each other along the rim of that cross section. So the force of surface tension can then be figured out by taking the coefficient times the length around the rim. That would of course be 2 pi times the radius. So we can say, okay, that's equal to the surface tension times 2 pi r. And let's find out what that is equal to. Surface tension is equal to 72.8 dyne per centimeter. That's of course for water at 20 degrees centigrade. Multiply that times 2 times the radius, and we said that the radius was 1 centimeter. That is kind of a big drop, but later on we'll then scale it down to smaller drops and see how that changes when the size of the drop changes. And let's see, I need a calculator now because I'm ready to calculate this. So we have 72.8 times 2 times pi and times 1. And that gives us, let's see here, 457.4 dynes. 457.4 dynes of force. Of course, the dyne is 1/100,000. So 1 dyne is equal to 1 times 10 to the minus 5 newtons, just as a reference. So dyne is the units of force in CGS units. Okay, now, what do we do next? Well, we know that we can find pressure inside a drop by using this equation. Let me write it here. Pressure by definition is equal to force divided by area. And so that implies that force inside the drop is pressure times area. So notice that I can set the force caused by the surface tension equal to the force caused by the pressure inside. Now, pressure times area, how do we think about that? Now notice that the pressure, of course, pushes in all directions radially outward from the center of the drop. But if I slice my drop into 2 slices, 2 half semispheres, or 2 semispheres so to speak, then I can notice that the force vectors pushing in all directions has a vertical component to that. So if we think of, because the ones in the opposite direction like this, they push outward so they don't cause any pressure in the direction of the force of the surface tension. So if I only consider the pressure in the direction of the surface tension, I only take the vertical components, and what we can then say is that that would be equal to force times the equivalent area. The equivalent area would be like the same as the cross-sectional area of the cut. So instead of taking the area of the semisphere, I simply take the area of the cut, which would be the effective area that only would be affected by the component of the outward force in the vertical direction. So this, instead of taking the area of the semisphere, I take the area of the cross-sectional cut. So I will then calculate this equal right here. So the force is equal to pressure times area, and we're going to set that equal to the force of the surface tension. Then all I have to do here is to find pressure, is to divide both sides by the cross-sectional area. So pressure is equal to the force of the surface tension, which we calculate over there, divided by the cross-sectional area. Of course, that's the force of the surface tension divided by pi r squared. Then all we have to do is plug in the numbers. So we get 457.4 dyne of force divided by pi times the radius. The radius is 1 centimeter, and we have to square that. And that would then be the increased pressure inside the drop. So divide by pi equals, and we get 145.6. 145.6. That would be dyne per square centimeter. Now, that doesn't mean a lot to us because we like to compare that to atmospheric pressure, which is in newtons per square meter. So we have to somehow convert that. So a dyne is this many newtons. So let's make the conversion here. So we want newtons at the top, dyne at the bottom. So 1 Newton is 1 times 10 to the minus, I'll take that the other way around since I put dyne at the denominator. So that would be 1 times 10 to the 5th dyne, because it's 100,000 dynes in a Newton. And then we have to account for the square centimeters. So we want square meters at the bottom, square centimeters at the top, so they will cancel out. And so 1 meter is 100 centimeters, but 1 square meter is 100 square centimeters. All right, so now what we get is to convert that to newtons per square meter, which is pascals, of course. We have to multiply times 100 times 10,000, divide by 100,000. It's like dividing by 10. So the pressure then is equal to 14.56 newtons per square meter. And that would be 14.56 pascals. That's the units of newtons per square meter or pressure. And then compared to atmospheres, since 1 atmosphere is equal to 101,300 pascals, if I then divide this by 101,300 pascals, I then express that in terms of atmosphere. So divide by 101,300, and we come up with a pretty small number. So this is equal to 0.001437 atmospheres. And so that would be about roughly 0.1% of the atmospheric pressure. So notice, it's not a lot of pressure built up inside a water drop, but remember, we took a water drop with a radius of 1 centimeter. What would happen if we now took a water drop that had a smaller radius? Now, to get a good picture of that, I'm going to rewrite this equation. Instead of writing f of st like this, I'm going to put down what that is equal to. So I'm going to take this thing again and rewrite that, and maybe I should use a different color so it makes a little more sense. So if I write the pressure is equal to the force of surface tension, which is gamma times 2 pi r, divided by the cross-section area, which is pi r squared. And notice the pi's cancel and one of the r's cancel. So this is equal to gamma times 2 divided by r, the radius of the water drop. Now that's actually a simpler equation, isn't it? Notice that as the radius gets smaller, the pressure will get larger. If I take 1/10 the radius, it'll be 10 times the pressure. 1/100 the radius, 100 times the pressure. So if I now take a water drop where the radius is only 1 millimeter, 10 times as small as that, 1/10 I should say, of the centimeter, then the pressure would be 10 times as large. So instead of being 0.1% of atmospheric pressure, now the pressure of a water drop would be 1% of atmospheric pressure. If I now make even a smaller drop, where the radius is equal to 0.1 millimeter, then of course it would be 100 times as much pressure, 1/100 the radius, 100 times as much pressure. So now the pressure inside that little drop would be 10% the pressure of atmosphere. You can see that the pressure really begins to build based upon the surface tension. So it's really amazing that the surface tension can have that much effect on the pressure inside the drop, especially when the drops get very small. So that gives you kind of a really interesting look at nature and the way drops respond in response to the surface tension.